Functions are just polynomials. And just like polynomials could be add, subtract, multiply, and divided, so can functions. What we have to learn is how to understand the symbolization and the terminology that goes along with it. So here's a little something about the algebra of functions. When I ask you to add two functions, we will use this notation. It is pronounced f plus g of x. It is the same thing as saying take the function f of x and adding it to g of x. This f minus g of x says take f of x and subtract from it g of x, always in the order in which it gives you the functions. F times g of x basically just says multiply the two functions together. And f over g of x says divide them. Now, one of the things you have to watch out for is the domains. The domains of each of these is going to be the intersection of the domains of each function. For the division, not only does it include the intersection, but you need to remember that g of x cannot equal 0. So you may have a little extra added to the domain. Let f of x equal 1 over x minus 2 and g of x equal the square root of x. Find f plus g, f minus g, f times g, and f over g, and find their domains. Okay, don't get real funny with these addition, subtraction, multiplication, division problems. A lot of times students want to try to do more work than they can or need to do in order to write it. Here's the sum. Now, is there more that you can do? There's a little bit, but it's really not worth it. You can just leave the answer like that. The next question is, what's the domain? Well, I said the domain was the intersection. So the first function, x cannot equal 2, because otherwise that fraction becomes undefined. And in the second function, x has to be greater than or equal to 0, otherwise that function does not exist. F minus g is just 1 over x minus 2 minus the square root of x. Same domain. For f times g of x, I don't even need that. You're just going to get the square root of x over x minus 2. Because this is over 1. And when you multiply them, you multiply the numerators, you multiply the denominators, and guess what? The domain is the same. Sorry, oops, that should have been a 2. That should be a 2, and that should be a 0. So x cannot be 2, and x has to be greater than or equal to 0. Last but not least, let's do the division problem. This is f over g. All right, that doesn't look very nice. So how am I going to make that look nicer? Well, one of the things I want to remind you is when you have a fraction within a fraction, you take the fraction in the numerator and multiply it by the reciprocal of the denominator. So I'm just going to get 1 over, I'll write the square root in front, square root of x, x minus 2. You don't even have to get rid of the square root. We'll just leave it as that unless you have some utter need to get rid of the square root. What's the domain going to be? Well, this time not only can x not equal 2, but we're going to say this time that x is greater than 0 and not greater than or equal to 0. I want you to think real hard about why I did not write greater than or equal to 0 for this particular solution. It's because this is now in the denominator. And if you put in 0 for x, you get 0 in the denominator, and that can't exist. Now let's find f plus g of 4, f minus g of 4, f times g of 4, and f over g of 4. Now remember that this is the same as f of 4 plus g of 4. So it'll make our lives a lot easier if we just figure out what f of 4 is. Well, f of 4 is going to be 1 over 4 minus 2 is 2. So f of 4 is 1/2. G of 4 is going to be the square root of 4, which is 2. So when I do f plus g of 4, I'm going to get 1/2 plus 2, which is 5/2. When I do f minus g of 4, I'm going to get 1/2 minus 2 in that order. So I'm going to get negative 3/2. F times g of 4, 1/2 times 2 is 1. And f over g of 4, well, 1/2 divided by 2 is the same as 1/2 times 1/2, which is 1/4. We can use graphical addition to show addition, subtraction, multiplication, division of functions. I'm going to do a simple one and show addition of functions. When we add functions, what we're actually adding are the outputs, or the y-coordinates of the functions. So in order to find f plus g, I'm going to start here at 0. I want you to know that the output of f of x is 0, and the output of g of x is 4. 0 plus 4 is 4, and that's where my orange graph is going to start. Here at 2, I want you to know that the output of f of x is 1, and the output of g of x is 2. And 1 plus 2 is 3. Here at x equals 4, the output of f is 3, and the output of g is 0. 3 plus 0 is 3. 5, 6, this is 7. At x is 7, the output of f is 2, the output of g is 1, the total output is 3. And over here at 8, 9, 10, the output of f is 1, 2, 3, 4, 5, and the output of g is 2. 5 plus 2 is 7. So this would be, the output of f plus g of x. All you have to do is add the outputs. In a composition of functions, one function will be substituted into another function. And we've already learned compositions of functions. We may have called it something else. There were times when we would give you problems like if f of x is equal to x and g of x is equal to x squared plus 1, or we'll say, if f of x is equal to the square root of x, find the solution when x is equal to x squared plus 1. And you know to plug x squared plus 1 into the other function. This is just another way of writing it. Both of these notations mean the exact same thing. And this is how it works. It says f of g of 2. Basically, you start with your input, which is 2. And it gets plugged into g of x. So if I plug 2 into g of x, out comes 5. 5 then becomes the input of f of x. And the square root of 5 is approximately, I don't know, it's like 2.41 or something like that. But the square root of 5 is what comes out. So the output of one function becomes the input of the next function. Let f of x equal x squared and g of x equal x minus 3. I want to find f of g and g of f. Remember, this notation looks like it says fog and goff, but it doesn't. It's pronounced f of g and g of f. So let's start with f of g. That says plug g into f. So instead of x squared, I'm going to write x minus 3 squared. Well, what's its domain? Its domain is just all real numbers. Because no matter what number you plug into either of the original equations, you'll always get a number out. Now let's find g of f of x. That one says plug f into g. So it says instead of x minus 3, you're going to do x squared minus 3. What's its domain? It is also all real numbers. Now let's find f of g of 5 and g of f of 7. So that says plug 5 into g first and get an answer. So g was x minus 3, 5 minus 3 is 2. We're going to take that output of 2, and now it becomes the input of f. Well, f was x squared, so x squared is 4. To find g of f of 7, that says plug 7 into f first. So 7 squared is 49. That output now becomes the input of g. So 49 minus 3 is 46. And that's the composition of functions. We can also do a composition of 3 functions. We can compose one function into another, into another, into another for as many times as we want. We don't usually do more than a composition of 3 functions. I want to find f of g of h. If f of x is x over x plus 1, g of x is x of raised to the 10th, and h of x is x plus 3. Now you got to do it in this order. We're going to put h into g first. So when I put h into g, I'm going to get x plus 3 to the 10th. Then after I put h into g, I'm going to put that output into f. So I'm going to have x plus 3 to the 10th in the numerator, and I'm going to have x plus 3 to the 10th plus 1 in the denominator. And that's a composition of 3 functions. Let's do a practical application of a composition of functions. A ship is traveling at 20 miles an hour parallel to a straight shoreline. The ship is 5 miles from shore. It passes a lighthouse at noon. Express the distance s between the lighthouse and the ship as a function of d, the distance the ship has traveled since noon. That is, find f so that s is equal to f of d. Well, we can relate the distance s and d by the Pythagorean Theorem. So if we say that there's a right angle over here, and you can't see it, and it doesn't really look like a right angle, but we remember from geometry that we're not allowed to assume anything. Over here at noon, the ship was 5 miles from the shore. And then it keeps traveling this way until it's at time t, and it's s units away from the lighthouse. So if we relate this using the Pythagorean Theorem, then we can say that s equals a function of d, and then we can use the square root of 25 plus d squared, because the Pythagorean Theorem would say that like 5 squared plus d squared is equal to s squared. So s would be the square root of this side, which is your 25 plus d squared. So there's my function. In the next part, we're going to express d as a function of t, the time elapsed since noon. So the distance that the ship has traveled in a certain amount of time. So we want to find g so that the distance is equal to g of t. Well, distance is equal to rate times time. So g of t is going to equal 20 miles an hour. That's the rate times time. Last, we want to find f of g. Sorry. I couldn't type that, so that's what I'm asking you to do. And then I want to know what the function represents. Well, to find f of g, we're going to plug g into f. So we're going to take 20t and we're going to plug it into the square root of 25 plus d squared. So it's going to be the square root of 25 plus 20t squared. Make that look like a t. What does that represent? It gives the distance of the ship from the lighthouse at some time t.